The concept of data gravity was introduced by Dave McCrory in 2010. At the time, McCrory was working at VMware, a company specializing in cloud computing and virtualization technology. It was not introduced through a traditional research paper, but rather through a blog post you are watching. The idea came about as he observed the challenges and dynamics involved in managing and processing large volumes of data, particularly in the context of cloud computing environments. Data gravity highlights how large sets of data can become a central force that attracts applications, services, and additional data, influencing the architecture and deployment strategies of IT systems. This concept has since become increasingly relevant with the growth of big data, cloud computing, and the decentralization of IT infrastructure. Imagine services, applications, and data like spatial bodies. Each has its own gravity, but data is most massive and dense. Therefore, it has the most gravity. Data, if large enough, can be virtually impossible to move and pull off the other spatial bodies, like a black hole. The two gravity tractors of the data are latency and throughput. The assumption is that the closer you are, i.e. in the same facility, the higher the throughput and lower the latency to the data. And the more reliant those applications and services will become on low latency and high throughput. On software workloads previous to AI, data gravity was quite strong. If there are terabytes of data stored in a particular cloud, the cost to transmit it elsewhere for processing is high. So many teams pick a cloud, such as AWS, Azure, or Google Cloud, and build everything on it. AI applications are reshaping the landscape of cloud computing and data management. Unlike previous software workloads where large data volumes fostered a strong gravitational pull towards a single cloud provider, the dynamics for generative AI differ markedly due to the disproportionate cost of processing over data transmission. Consider the current prices. Transmitting 1 gigabyte of data costs 10 cents, while processing this data, equivalent to approximately 250 million input tokens, costs about $125, employing GPT 3.5 Turbo. For GPT-4, the price is an order of magnitude higher. Hence, transmitting costs cents while processing on the best performance model costs thousands. Also, the use of AI providers attack one of the tractors of the data gravity, the latency. When AI is processing, the latency is high enough that sending tokens of text or image across the internet usually doesn't impact the overall latency of the process. So transmitting data is not a bottleneck. This indicates that, even when developing software primarily on a specific cloud provider, it remains entirely feasible to transmit LLM prompts to OpenAI, Together.AI, Anthropic, and others, or alternatively, Azure, AWS, or Google Cloud, in order to receive a response. The motivation to exclusively rely on a single monolithic cloud platform is diminished compared to previous circumstances. The state of the art in AI is very volatile. For instance, switching between LLM providers might seem quite annoying at the moment, but not impossible. However, moving databases is a tougher task. For example, once a lot of data is stored in a particular vector database, switching to another one can be quite complex. To wrap up, data gravity is decreasing due to AI interactions. Developers and companies must increasingly leverage a mosaic of SaaS offerings, integrating services from across the digital sphere. Voice has been generated by AI, and it is not a real person.